Now it's time to discuss the advantages of using this type of equipment. And we're going to contrast what it's like to measure molecules and solvents, which is what we've been focused on, versus free atoms in a gas phase. So first, let's direct our attention to molecules. All of this should be a review for you. We recall that there are two different types of excitations possible in a molecule that concern us in this class. The electronic excitation, which would be represented by going from this line to one of these thick dark lines. And then there are the vibrational excitations, represented by jumps to these thinner lines. And of course, both of these excitations can happen at once, in which case we have a vibronic transition. And we learned all about these in the past few lectures. And these different transitions give rise to spectra that look like this, where each of these peaks that look kind of like fingers just represent different vibrational transitions on top of the electronic transition itself. And so all of these different peaks are associated with just one electron being excited. The only difference is the degree of vibrational excitation on top of that electronic excitation. Again, this should sound very familiar to you by now. We also covered that when we're in a polar solvent, all of these peaks will smear together and create one broad peak or hump-like figure. And these humps can extend over potentially hundreds of nanometers. And this can be a problem for solutions with more than one chemical that absorb in a similar wavelength range, because let's say there's some other chemical whose peak absorption happens over at this wavelength. Well, you might think that that's not a big problem, because this peak here is nowhere near this peak over here, but the issue is that these peaks can extend, again, over hundreds of nanometers, so there's a very real chance that we'll get this convoluted situation where different peaks are overlapping with each other, and the instrument can't distinguish what's absorbing what wavelengths. All it can do is measure the total absorption of light at any given wavelength. So it would actually interpret, say, this wavelength as being absorbed as the total sum of the absorption from both of those chemicals. And so these two peaks might combine to create some larger peak that looks like this, which is pretty much impossible to analyze. So it would be great if we could have more narrow peaks that had much lower chances of overlapping, even if we have numerous chemicals in solution. But that's rather difficult when we have spectra that look like this, which again arise from all of the different possible excitations in a molecule, which in turn are related to all those vibrational options that are close together in energy. But if we were to put this molecule in a high enough temperature environment, we can break all of the bonds and vaporize it into just gaseous atoms of carbon, nitrogen, and hydrogen. And free atoms in the gas phase are simple. They don't have bonds anymore, so there's no vibrations. The only transitions possible are electronic between the atomic orbitals. And these are the orbitals you learned about in Gen Chem, like S and P orbitals, spheres and dumbbells, not those giant delocalized MO structures we talked about. So take sodium, for instance, which is what these energy levels here correspond to. Its highest energy electron is in a 3s orbital, and spectroscopists figured out the wavelengths of light that cause excitations ages ago. So we already know that 590 nanometer light is just enough energy to cause an excitation of this electron to the higher energy 3p orbital. 330 nanometer light, which is shorter and thus more energetic, can get that electron up to the 4p orbital, and 285 nanometer light can get it up to the 5p orbital. But notice there are no vibrational transitions sandwiched in between. And so the spectrum of these different electronic transitions looks like this. Each of these peaks corresponds to one of these transitions here. And they're sharp and they're narrow, unlike this situation, where all of these peaks are related to just one single excitation of an electron. The differences are vibrational levels that are being reached. But in principle, further to the left at shorter wavelengths and higher energies, there's another series of finger-like peaks that are associated with the vibronic transitions at the S2 electronic state. So again, much simpler when we deal with atoms. And so that's why we do this. One other quick note, The different intensities of absorption are due to different absorption and transition probabilities within this atom here. We've seen the idea of probabilities before when we were dealing with UV-Vis and fluorescence. Just because light can be absorbed does not mean that it will be absorbed. If you haven't written that down before, write it down now. Just because light can be absorbed doesn't mean it will be. So even if we shined in equal intensities of each of these three wavelengths here, this wavelength is just absorbed more often than this one, which in turn is absorbed more often than this one. And that's why these peaks go down in height as wavelength decreases and energy goes up. So having said all that, let's write down some notes finally. Now I'll start by reminding you that this branch of spectroscopy is called atomic spectroscopy. At this point you should appreciate why it's called atomic spectroscopy, because we convert everything into atoms and we just went over why we would do that and what the advantages are. Now there are two types of atomic spectroscopies that we will cover in this class. There's using it in absorption mode and there's using it in emission mode. So we're going to start with absorption. We will call this atomic absorption spectroscopy. Atomic absorption spectroscopy. Or AAS. In this technique, we measure the transmittance of light and thus also the absorbance of light from a device known as a hollow cathode lamp. So here's how we're going to write that. Measure trans/absorbance. Measure trans/absorbance of hollow cathode lamp light. Hollow cathode lamp light. As for what the hollow cathode lamp is that we've seen mention of a couple of times so far, well, this is a lamp that is designed to emit a light that is absorbed by a very specific element. Emits light that is absorbed. Emits light that is absorbed. By a specific element. So we saw in that instrumental video that the lamps are labeled by specific elements, like iron. An iron lamp shines in lights of wavelengths that only the iron electrons should absorb. They're compatible with the iron's energy levels and delta E's as opposed to, say, copper's. From here, things work like other absorbance experiments. We shine in light from that hollow cathode lamp. If the element that corresponds to that lamp is present, then it will have the energy levels that are compatible with that light, and the electron can absorb the light and be excited to a higher energy orbital. And we will write a note that excitation is primarily due to light absorption. Excitation primarily due to light absorption. And I write the word primarily because we're about to learn that there are other ways that the electron could be excited potentially. But in these experiments, the major way that the electrons are excited is through absorbing this light that we're shining in. And we have the same condition that we've had since the beginning of spectroscopy. The energy of the light must be equal to the delta E between the levels in the atom. But these are well defined for atoms. Again, spectroscopists have already studied this. We know what lights are absorbed by different atoms. And so we design those lamps to only emit those particular lights for that particular element. So this is the theory behind an AAS experiment. As for what we do with it analytically, well, a perfectly good option is potentially to just use a calibration curve. At this point, we're just looking at Beer's law. As the concentration of absorbing atoms increases, so too should the degree of light absorption. And we can make a calibration curve with standards, plug in our unknown, solve for concentration. Now, with all of that said and done, I'm going to erase all of this and then discuss the theory behind an emission-based experiment. And we would call this type of spectroscopy atomic emission spectroscopy. Atomic emission spectroscopy, or AES. Now, we've talked about emission-based experiments before, right? In fact, earlier today, we wrapped up fluorescence. But the difference between this type of emission and fluorescence emission is fluorescence emission was induced by absorbing a photon, which excited the molecule, and then the excited molecule would relax and release light. In this type of experiment, we will not be shining in any light at all. There is no lamp. We measure the emission from relaxing electrons that were excited from the high temperature environment. So measure emission from relaxing electrons that were excited by the high temperature environment. That were excited by high temp environment. Because while there might not be a lamp, we're still vaporizing everything in fire and converting everything into gaseous atoms. And the reason why that high temperature can cause excitations is because hot atoms collide, and sometimes those collisions have enough kinetic energy transfer associated with them that the electron can be excited to a higher energy orbital. So let's write that, and then I'll try to describe that a bit more clearly. Hot atoms collide with enough energy to excite the electron. Now let me try to explain this collision excitation concept a bit more clearly. Okay, first of all, let's review what type of energy is transferred when two bodies collide. The type of energy is kinetic, right? The energy of motion. So let's start with the most basic problem possible, where we just have two balls, one of them stationary and the other one bumps into it. This ball transfers some of its kinetic energy into this one, and so this one starts to move faster. Now let's reset. Imagine this time the ball hits this one, and the ball's an atom. And this atom takes that energy that's being transferred into it, and instead of converting that into kinetic energy and moving faster, it puts that energy into the electron, and the electron just absorbs the energy and goes to a higher energy orbital. In this case, the condition for that to happen is that the kinetic energy being transferred into the atom must be equal to the difference in energy between those orbital levels. So we still have that conservation condition. Energy must equal delta E. It's just this time the energy is not coming from light, it's from this collision. Now at room temperature, collisions between atoms and molecules do not have the kinetic energy to cause these excitations. But at 2500 degrees Celsius, where everything's moving around with a lot more speed and less kinetic energy, well, it can happen. It's not a guarantee to happen, but it can happen. So with that in mind, let's get back to our notes. Let's say we have some atom with these two energy levels. The electron is, of course, starting in the lower energy level, but then a collision happens that has enough energy transferred into this electron that we're able to get an excitation to occur. Notice I'm using the squiggly arrow. We recall that squiggly arrows represent that the energy transfer does not involve light. In this case, our excitation is from the high temperature collision. But as we've learned, what goes up must come down, and maybe the way that electron makes its way back down is through the emission of light. Light emitted as electron relaxes. And our standard energy condition is still in play. Whatever this change in energy here is, it must be equal to the energy of the light that's being emitted. So for example, let's say we have a sample of lithium atoms. Well, the delta E between the levels in lithium, at least between its valence electron, which is in the 2s orbital, and its closest in energy vacant orbital, which is the 2p, the difference in energy is equal to 2.961 times 10 to the minus 19 joules. And this in turn must be equal to the energy of light that is emitted. And just to be very specific, let's make this delta E term the absolute value of delta E, because technically the change in energy that the electron is experiencing is negative. It's going down in energy. But the energy of the light that's being released is positive. And utilizing the equation that we learned at the very beginning of spectroscopy that relates energy to wavelength, we can determine that the wavelength that is going to be emitted by lithium through this relaxation process is equal to 670.8 nanometers. 670.8 nanometers. And this wavelength is not only in the visible light spectrum, but it's in the red portion of the visible light spectrum. Remember the color of the flame in the instrumental video when I started burning a lithium solution? That distinct redness is the 670.8 nanometer light that's being emitted from excited lithium atoms. And that's what gave it such a specific and distinct color. And so that's the logic of an emission experiment. So we have AAS and AES covered. Now, what do you think is the next logical question to ask ourselves? To me, I would ask, why would we use one as opposed to the other? So let's erase this and then get into AES versus AAS.